Hello everyone. I'm Dr. Akhila Rupesh. I'm a postdoctoral fellow at Philips Research. In this particular video, I will be talking about two different instruments used to determine flow angularity in aerodynamics. So the presentation is entitled Determination of Flow Angularity with Unique Flow Analysis. So, in aerodynamics, we study airflow behavior under different operating conditions, such as change in velocity, pressure, and flow directions. This is important because real world engineering problems like aircraft performance, turbine efficiency, or high speed flows are often very complex. While numerical and theoretical models help us predict these behaviors, they are based on assumptions and simplifications. Because of this, they are not always fully reliable, especially for highly complex or turbulent flows. Therefore, experimental validation becomes essential. It helps us verify whether our theoretical predictions are accurate and applicable in real conditions. In aerodynamics, experiments are generally carried out using three main methods or approaches. The first approach is direct measurement. Here in direct measurement, we directly measure flow properties like pressure, velocity, and temperature using instruments such as a probe or a sensor. This particular method, in most of the cases, gives quantitative as well as highly accurate data. The second measurement approach is analog measurement. In this method, we use indirect techniques or analog method to represent the flow behavior. It is useful when direct measurement is difficult or impractical. The third method or the third approach is flow visualization. This technique helps us see the flow patterns using methods like smoke, dye, or particle testing. It provides qualitative understanding of the phenomena like vortices, separation, and turbulences. So together these three approaches help us get a comprehensive understanding of aerodynamic behavior and helps bridge the gap between the theory and the real world performance. So in aerodynamic measurements, the shape of the sensing element plays a crucial role in determining the sensitivity. Instruments with a cone-shaped or a wedge-shaped tips are usually highly effective because they respond strongly to its changes in flow direction and pressure. As the cone or wedge angles increases, the sensitivity of the instrument also increases. This means we can detect small variations in the flow more accurately, leading to better measurement precisions. However, increasing this angle indefinitely is not a practical approach. At very large angles, flow separation as well as detached shock waves can occur, especially in high speed flows. Additionally, tunnel blockage effects become significant. It disturbs the flow field and reduces measurement accuracy. So because of these limitations, we cannot simply rely on large angle cones or wedges for precise 3D measurement. To overcome these challenges, specialized multi-hole flow analyzers are used. So here in this particular section, I will be discussing about two different flow analyzers. The first one is a 4-hole flow analyzer and the second one is a 5-hole flow analyzer. So this particular flow analysis which I will be discussing helps to achieve accurate flow characterization without relying on extreme geometries, making them ideal for experimental aerodynamics. So first we will discuss about the 4-hole flow analyzer. So the 4-hole flow analyzer is a multi-pot pressure probe which is used to measure flow characteristics in a flow stream or a fluid stream. It consists of 4 strategically placed pressure prods that senses variation in pressure due to the flow directions. By comparing the pressure differences between these pods, we can determine the flow direction and velocity components in the stream. This makes the probe very useful for understanding how the flow is behaving locally. This 4-hole flow analyzer can be widely used for aerodynamic testing, turbo missionary flows, as well as internal experimentations. One of its key capability is the measurement of yaw angle, which indicates horizontal deviation of the flow direction. In addition to the flow direction, the probe also helps us to estimate total pressure as well as static pressure. So overall, this four-hole flow analyzer is a good balance between simplicity and measurement capability, making it a practical tool for experimental aerodynamic application. Now, so this particular figure shows how the holes have been placed in the four-hole flow analyzer. So now we'll talk about the measurement capability of the four-hole flow analyzer. This particular probe is preliminarily used to determine the yaw angle, which represents the direction of the flow in the horizontal plane, which in turn helps us to find the flow angularity. By analyzing how the flow approaches the probe, we can understand its angular deviation. So in addition to the flow direction, the probe can also measure total pressure directly. With proper calibration, it can further estimate the static pressure with few mathematical calculations. So using this pressure measurement, we can also calculate the velocity magnitude of the flow. So overall, the probe gives us both directional as well as quantitative information about the fluid flow. Now coming with the working principle of this particular flow analyzer, the four-hole flow analyzer consists of four pressure pods, as you can see in the particular figure, which are arranged symmetrically around tip of the probe. When the probe is placed in a flow field, each pod senses a slightly different pressure depending upon the flow direction. If the flow is perfectly aligned, the pressure measured is symmetric. However, when the flow has an angular component, it creates pressure difference between the pods. So these pressure differences are directly related to the flow angularity. By comparing the pressure from the different pods and using calibration data, we can accurately determine the yaw angle. Uh, Essentially, this particular probe works on the principle of flow direction alters the pressure distribution around the probe head, and this variation is used to extract meaningful flow parameters. So this particular figure, which is shown on the right side of the slide, helps us to get a clarification about how the terms have been explained in this particular calculation part. So now let's explain how flow angularity of the flow is determined using this particular flow analyzer. So flow angularity basically refers how much the flow is deviating from its main direction. We express this particular deviation as in major cases as two components, the yaw angle and the pitch angle. So the yaw angle represents the horizontal deviation of the flow, and the pitch angle represents the vertical deviation of the flow. Now, if we want to determine these angles, namely the yaw angle and the pitch angle, the pressure difference ratios have been used. So, for yaw angle, P1 and P3 pressures are used, and for pitch angle, P2 and P4 pressures are used. So, these are the equations which are noted down in the slides, which help us to determine the yaw angle as well as the pitch angle. Now, in this particular figure, it illustrates how flow angularity is determined with respect to this multi-hole flow analyzer. So, if you observe the incoming flow, which is shown moving from left to right, ideally the flow would be perfectly aligned with the probe axis, but in reality, it can deviate in different directions. Now, look at the coordinate system. The y-axis represents a vertical direction. The z-axis represents a lateral direction. So, the probe is placed at the center, acting as a reference point. Now, we'll understand the two major angles, which is yaw angle, which gives a horizontal deviation, and the pitch angle, which gives the vertical deviation. So, the yaw angle, which is shown in red, it represents the sideways deviation of the flow in horizontal plane. A positive yaw angle means the flow is deviating towards the right angle of the probe. This is essentially rotation about the vertical axis. Now coming to pitch angle, which is shown in blue color, it represents the upward or the downward deviation of the flow. A positive pitch angle represents the flow is acting upwards. So this corresponds to rotation about the lateral axis. Okay, so this is about this particular figure. Moving on to the calibration process. So calibration is very important once we consider any instrument. So here once we talk about calibration process of our 4-hole flow analyzer, first the probe is placed in a controlled and non-flow field, typically inside a wind tunnel. So in this particular setup, what we will do is the flow properties such as velocity and direction are already known with high accuracy. So now we will start varying the flow angles. Systematically, we will start varying the flow angles. This means we can change the yaw as well as the pitch angles in a controlled manner step by step so that the probe experiences different flow directions. At each angle, the pressure from all the 4 pods are recorded. So finally, using this data, we will be able to generate a calibration curve. This calibration curve relate pressure coefficient ratios which comes from the measured pressure and the actual flow angles which is from the yaw and the pitch angles. So essentially we create a mapping between what the probe measures and what the actual flow conditions are. Okay, now this particular slide simplifies how the calibration, how the total setup looks like. First, we have to measure all the 4 pressures using the flow analyzer. Then we will have to compute it using the normal calculation parameters. Then we will have to go with the calibration curve that has been explained previously. And we will be able to get the result flow speed as well as the flow angularity. That is flow alpha and beta, which represents the flow angularity, can be determined. So these are the mathematical formulation part. So this is a detailed mathematical formulation. So simplified version can be used to plot the curve. So here it will be showing how the detailed mathematical calculations looks like. So we will be able to calculate coefficients of all the parameters, total pressure, static pressure, pitch and yaw, using all the 4 pressures that we have already got from the four-hole flow analyzer. Now, coming to limitations of this particular instrument, there are few limitations. The first limitation, the probe is limited to most of the cases we will be able to use this probe in 2-dimensional flow measurement, though it can be used up to an extent for 3-dimensional, but accurate results may not be obtained. So in most cases, it is limited to a 2-dimensional flow measurement. So it can accurately measure yaw angle, but it cannot fully resolve the complex 3-dimensional flow structures once we are comparing with a 5-hole probe. So when the flow has significant vertical component, it becomes there are restrictions in the capability of the instrument. Now, secondly, once we are talking about the limitation, the second limitation is accuracy decreases at higher flow angles. As the flow deviates more from probe axis, the pressure distribution becomes highly non-linear. This makes it difficult to interpret the reading accurately, leading to increased measurement errors. Now, the third limitation, it requires careful calibration. Since all the measurement depends on pressure differences, even small errors in calibration can significantly disturb the final output. So proper calibration across the entire range of flow angle is essential for the reliable data. So the final part, it comes with the sensitivity of manufacturing imperfections. So any misalignment or any manufacturing defect will completely affect our intention of getting a proper flow and its related measurement. Now let's discuss about the 5-hole flow analyzer. So this is a figure which explains how a 5-hole flow analyzer looks like. So basically, a 5-hole flow analyzer is an advanced multi-pot pressure measurement device which is designed especially for a 3-dimensional flow properties, for determining 3-dimensional flow properties. So this particular instrument, as I've told, when comparing to the previous one or when comparing to other probes which are available for measurements, this is more accurate. We will be able to use this particular instrument for measuring the flow accuracy of more complex problems. So it is extensively actually used in aerodynamics as well as in experimental fluid mechanics. where we have to understand the detailed flow characteristics, and it is crucial, and where the situation is crucial to understand the performance, to take the performance analysis as well as the design analysis. Now, and the key advantage of this particular instrument is we will be able to measure yaw angle, which is the horizontal deviation of the flow, pitch angle, which is the vertical deviation of the flow. Along with it, we will be able to measure the velocity magnitude as well as the pressure component. So it provides us a complete picture of the flow in 3 dimension. Now, coming about the construction part, it is having 5 holes. Each probe is having 5 holes, one at the center and remaining 4 on the circumference of the probe. So this is how it looks like, one at the center and the remaining 4 holes which are given equally spaced at the circumference. Now let me explain about the measurement capabilities of this 5-hole pressure analyzer or flow analyzer. This 5-hole device, 5-hole probe is designed to provide a complete 3-dimensional description of the flow field. So first it can determine the yaw angle, which represents the direction of the flow. This tells us how much there is deviation sidewise in the flow. Next, it will be able to measure the pitch angle, which represents the vertical deviation of the flow. So together, yaw and pitch define exact direction of the flow in 3D space. In addition to the flow direction, the probe also measures total pressure directly from the central pot. With proper calibration, we will be able to measure the static pressure using some calculation part, mathematical calculation part. So total, it will help. It will be so essential for aerodynamic analysis. Now, using this measured pressures, we will be able to calculate the velocity magnitude of the flow. So most importantly, since both yaw and pitch are known, the velocity can be resolved in 3 components, x, y, and z directions. So this makes a 5-hole probe highly suitable for complex as well as 3-dimensional flow field, especially for wakes, high curve flow regions, and turbo machinery applications also. Now, coming to the next slide, we'll discuss about the working principle and how the angularity, flow angularity is determined using this particular 5-hole flow analyzer. So, this 5-hole flow analyzer operates based on the idea flow direction affect the pressure distribution around the tip of the probe. So, when the flow approaches the probe, if it is perfectly aligned, the pressure distribution across the surrounding pods remain symmetrical. However, when the flow is inclined either in horizontal direction or in the vertical direction, it creates a variation in the pressure at different pods. So the probe works by comparing the pressure from all the 5 pods. So central pod gives us the reference pressure, which is typically in most of the cases the total pressure, and the surrounding pods experiences different pressures depending on the flow direction. Now, if there is a pressure imbalance between these pods, it directly indicates that the flow is not aligned with the probe axis. A difference between side pod indicates the yaw, which is the horizontal inclination. Difference between the top and bottom pods indicate the pitch, which is a vertical inclination. It almost works similar with the 4-hole flow analyzer. So by analyzing these pressure differences and using calibration data, we will be able to we will be able to get accurate flow directions in multiple planes. So the flow angularity here, it represents how much the flow is deviating from the main axis, and it can be again expressed as yaw angle as well as pitch angle. It is same when considering with the 4-hole flow analyzer. To determine these angles, that is yaw angle as well as pitch angle, so we look at the pressure differences between the opposite pods on the probe. So for yaw angle, we compare the pressures between the left and right pods. So if the flow shifts sideways, one side experiences higher pressure than the other. The left-right pressure differences directly indicate us the horizontal deviation, which is the yaw. Now coming with the pitch angle, so we compare the pressures between the top and the bottom pods. So if the flow moves upward or downward, it creates a pressure imbalance. So this this top bottom pressure differences helps determine the pitch, which is a vertical variation. So this is how the flow. So this particular figure explains the yaw as well as the pitch that I have been explaining in the previous slide. And these are the flow. These are the mathematical formulations which help us to determine the yaw coefficient as well as the pitch coefficient. Now, coming with the calibration curve. So calibration curve is most important while we are using these instruments. Mm, 1 second. Yeah, now the first calibration, you will be able to see the yaw calibration curve on the left side as well as the pitch calibration curve on the right side. So the yaw calibration curve, which is on the left side, we will first see to that particular curve. The horizontal axis here, it represents the yaw angle in degrees. The vertical axis represents the pressure coefficient ratios. So as you can see, the curve shows a systematic variation of the pressure coefficient with yaw angle. When the yaw angle is 0, the coefficient is also 0, indicating a balanced pressure. As the flow deviates to either side, the pressure differences increases and the coefficient changes accordingly. The relationship is almost linear with a certain range, which makes interpolation easier. Now, coming to the pitch curve, which is on the right side, the horizontal axis represents the pitch angle and the vertical axis represents the pressure coefficient. Similarly to the yaw, at zero pitch, the coefficient is 0. As the flow moves upward or downward, the coefficient changes. So again, we observe a smooth and nearly a linear relationship over the operating range. So in short, this is the measurement and processing of a 5-hole flow analyzer. We have to pressure all the 5 pressures. We have to compute the coefficients. Then we will have to go with the calibration curve and obtain the flow angularity. We will be able to determine the flow angularity. Now coming to the advantages of this instrument along with the disadvantage comparison with the 4-hole flow analyzer. Now, coming to the advantages first, one of the biggest advantages is that it can measure the complete three-dimensional flow field. So, unlike a four-hole probe or a simpler probe, it captures both yaw and pitch angles along with the velocity component, which gives a full idea about the flow behavior. Second, It is highly accurate in angular flow measurement because it uses multiple pressure pods and detailed calibration. It can precisely detect even small changes in the flow. Then coming to the third advantage, it is mostly suitable for high directional as well as complex flows. This make it like ideal for applications like flow in high speed industries, turbo machinery, where there is a constant change in the flow direction. Now coming with the final advantages of this instrument, it is widely validated in experimental aerodynamics. So it has been extensively used and tested in research industries, making it a trusted instrument, reliable measuring tool. There are few limitations also, since it is having more number of pressure holes, the calibration process is more complex. So all the since it measures a three-dimensional flow, calibration must be performed over a wide range of yaw and pitch angles. This is more time consuming, as well as there will be intensively a high number of data, which makes the process more complicated. Then again, the cost is very high when comparing to the simpler props. Again, there are complications with the design. Then manufacturing, there are complications in manufacturing. Precision manufacturing has to be done. Then more advanced data acquisition systems are required. Most importantly, errors, the chances of occurring errors are more high. So if there is misalignment, there are chances of errors. If there are any manufacturing imperfections, then also even small deviation in the pod size will be resulting in the reduced accuracy of the result. And data reduction requires a computational effort. So it is actually a big process. Even if you are getting the data, analyzing the data from the obtained result, it is a time consuming as well as a complex problem. So coming to the conclusion about this flow analysis, which we have explained in the previous slide. In aerodynamics, flow measurement is crucial. Mm, there are many instruments that we are using for a long period of time. Even there are numerical methods, even there are theoretical methods which validates these results. It is most important that the design of this instrument has to be done with utmost care. So once we are comparing both the instruments that we were discussing here, the four-hole probe mainly it is used for two-dimensional flow analysis. It will help us to determine the yaw angle and velocity, but it cannot fully capture the vertical flow variations. So when comparing to that, the five-hole provides a complete three-dimensional flow characterization. It can measure both yaw and pitch angles along with the velocity component in all directions, giving a much more detailed understanding about the flow. So when it comes to accuracy, especially in the complex flows, the five-hole pressure probes will be performing in a better way when comparing with the four-hole. So it will be giving high angular as well as three-dimensional flows because it can resolve flow variations in multiple planes. Now, coming to the calibration requirements, if you are looking at the calibration requirements, the four-hole flow analyzer requires simpler calibration methods when comparing to the five-hole flow analyzer. As I've told, the calibration process is extensively larger when comparing with the four-hole flow analyzer. And data interpretation is also more straightforward when comparing with the five-hole in the four-hole flow analyzer. So in short, the four-hole flow analyzer is a simpler and it's suitable for basic flow analysis, while the five-hole flow analyzer will help us to solve more complex. It will be providing us high accuracy and complete three-dimensional flow information, especially in challenging flow conditions. So, so far, Dr. Lal and I have been working with this particular area for the last few years. Last more than 8 years, we have been working. So we have gone with few patents, publications, and many conferences have been attended, and this work has been presented. So the part of this work has been presented. So it starts from very very scratch. We started with very small, simpler props. We started developing these props and it came up to five-hole flow analyzer. So the five-hole flow analyzer, we will be able to increase the number of holes for our upcoming complex flow determination methods. So here, these are the related works and a few research milestones that we have achieved so far, the patents, publications, and some abroad conferences as well as the normal